Good morning, class. This is Sir Alex again, and welcome back to our class for today, Physics 2. And today we'll be moving on to a different topic. Today we'll be discussing about electric current. So previously we've discussed capacitance, capacitors, and and everything that is related to capacitors and how energy is stored in capacitors. Now we'll be discussing about the electric current. Okay, so to start, let's discuss what is electric current. So previously we've discussed that when there is a potential difference between the terminals of a source or a voltage source, as for example in a battery, charges would flow. So if there's a this potential difference results in the movement of a charge q, and that movement uh, over time or per unit of time is what we call electric current, which we usually denote with letter I. So electric current is the amount of charge passing through at any point in a conductor per unit time. We usually use the equation I is equals to the charge divided by time, where Q, or where I is the electric current, which we use the unit coulombs per second, or we also use the unit ampere, which we denote with letter A. Q is, as we have known, is the charge in coulombs, and T is time in seconds. So simple as that, electric current is the amount of charge passing through uh, or flowing per second or per unit time. In this case, we use second as a unit for time. So electric current, André Marie Ampère is a French scientist and mathematician that first described the current as a continuous flow of electricity along a wire. And he is the person where the unit ampere is named after because of his contribution in electrodynamics. And he is considered as the Isaac Newton of electricity. As you guys should know, Isaac Newton, or Newtonian law of motion, Isaac Newton helps identify the Newtonian motion, and Andre Ampere used basically Newtonian motion in dealing with the movement of electrons. That's why he founded the science of electrodynamics, which is the study of charges in motion. Electron means electrons, dynamics means there's movement. And although it is possible to use the Newtonian motion in dealing with electrons and other charges, ultimately, in the end, some physicists rather use quantum motion because they are in quantum state, and we can predict more accurately the motion or the movement of small charges like electrons and protons using quantum mechanics. But we're not talking about quantum mechanics today. We'll just be discussing about the movement of electron, and we'll be using a lot of Isaac. We'll be using the Newtonian motion in understanding electric current for this lesson. Okay, but yeah, Andre Marie Ampere, it's because of him that we managed to start studying the movement of the charges of electrons. So let's first discuss about conventional current and electron current. So these are two types of current. They're basically the same, it's just a difference in their movement. So Benjamin Franklin is the one who coined the terms positive and negative charges. And Benjamin Franklin used the conventional current. So conventional current is basically the flow of positive charges from positive terminal to the negative terminal of a source. As an example, you have here. So we have your source right here, or basically your battery can be your source. You have positive terminal and negative terminal. So for a conventional current, there is a movement of the positive charges from your positive terminal of your source going to the negative terminal of your source. On the other hand, when we discovered electrons, years after Benjamin Franklin, we discovered that it's actually the electrons that move, not the protons. So we started using the term electron current, which is the flow of electrons from negative terminal of your source to the positive terminal. So they're basically the same. We still use conventional current because there's a lot of research studies that have been conducted using the conventional current and the research stance and everything that is found on those research stance. So we still use conventional current as well. So in the end, they're basically the same. We are just using the direction. The only difference is the direction and which electron or which particle is moving. Conventional current, it's the positive charges moving from positive to negative, while electron current are the electrons move are uh, electron current is basically the electrons moving from negative to positive. Next, let's discuss about direct current versus alternating current. You guys may have seen these or may have heard of AC/DC. So AC is alternating current, DC is direct current. AC/DC is also a band, but that's a different story altogether. So when we talk about DC, it's direct current. Direct current is a current that travels in one direction at all times. So direct current is usually supplied by cells or batteries, and we commonly use direct current when we use energy stored in cells for flashlights, calculators, automobiles, and even cell phones. Alternating current is from the word itself is a current that changes direction at regular intervals. Normally, the changes in direction happen 60 times in a second. And alternating currents or AC are usually produced by AC generators and distributed by electric companies such as Meralco in the Philippines. And it is what most houses or household appliances use in order to operate. So you have fridge, um, your irons, your television uses AC generators or AC current, alternating current in order to use the energy to for them to start working. So that's just the difference, okay? Nothing really big in there. This time we're gonna move on to what we call drift velocity and current density. So we'll be using most of our time discussing about drift velocity. So buckle up because there's a lot to discuss about drift velocity, which is important for you guys to understand because will be using drift velocity in order for us to measure current. So earlier we discussed what current is. Current is basically the amount of charge moving through a conductor over a specified of time or basically per second. So we usually denote the equation of current or electric current as I is equals to Q over T. But we can also measure or we can express current using drift velocity. But before I'll show you the equation on how we measure current using drift velocity, let's discuss first what is drift velocity. So electric current can be expressed in terms of drift velocity. Drift velocity is the average velocity attained by charged particles, such as electron in a material due to electric field. This is a very, let's say, oversimplified meaning of what drift velocity is. I think we'll understand more about drift velocity if I explain what is happening. So first, let's consider this simple circuit that we have here. And this simple circuit has a current of 5 amperes moving from the positive to the negative. And we know in this circuit that the electrons, so these red dots right here, let's consider those as electrons. They are being attracted because of the battery, and they are moving from left to right. They are being attracted to the positive terminal of your source or your battery. So we know that when something gets attracted, they accelerate. As for example, if we have a ball and we drop it from the sky, we know due to gravity that the ball will get attracted to the center of the earth, or basically the surface of the earth. And we know that as the ball, when we drop it from a certain height, it accelerates going downward. Same scenario is happening to these electrons right here. As they get attracted by the positive terminal of the battery, they accelerate. However, if they accelerate, meaning they go faster and faster, right? If they go faster and faster, since we define current as the charge moving per second, if this movement is faster, does that mean that the current should be faster? Or not faster, should be higher? Normally, under certain conditions, we would assume that. However, that is not that is not happening in our scenario. In our circuit, we know that the system would want to keep a constant voltage or constant current. So these electrons, despite accelerating, our current 5 amperes stay the same, or it stays constant. So what is happening? If our electrons are moving faster, should move faster and faster, why why is our current the same? Why does it not increase? So the reason for that is because if we remove the battery, okay, so let's say we remove this battery of our circuit right here, we would assume that these electrons would stop moving, they would keep at rest, right? But in reality, they actually are not at rest, meaning they are actually moving. So to point it simply, the electrons are never, not never, are not at rest in this scenario. This the assumption that if we remove the battery, the electrons would start moving is actually false. What is happening is that the electrons are moving in a random zigzag motion. So they're colliding with themselves, and they're colliding with the positive ions present in the conductor. So if, for example, we have a picture right here, we have our electron right here, this red dot. Let's say this red dot move going this way, and it bounces or collides with a positive ion, and it bounces this way, goes this way, and bounces back until it reaches at this point. So when there is no battery inside our conductor, the electrons move randomly, they keep moving. So you may ask, sir, if they are moving, why is there no current if we remove the battery? Because we know if we remove a battery or voltage source in a conductor, there will be no current. That is true. But if current is the movement of electrons over time, and you just said that electrons are moving even if there's no battery, how come there's no current? It's because if we looked at these movements over time, these electrons essentially stays at a certain spot. So what do we mean by that? So as these electrons move randomly, it's because of the randomness of their movement, the randomness of their collision, and the randomness of their zigzag pattern. And what we're gonna see is something like this. So there's an area where the electron just keeps moving around and never leave this area right here. And if these electrons keep moving and keep bouncing in this area, so let's say this red dot right here is our electron, and it keeps bouncing, it keeps moving. As you can see, this red electron does not really leave this yellow circle where it is encircled. So in the end, what we can say is that it stays the same because it stays in that area. It just keeps in that area. Therefore, we can assume that the electron ultimately is not moving. And this is happening to all the electrons. If this is happening to all the electrons, meaning all the electrons are not moving. So if there is no battery hooked up in our conductor, all our electrons basically just bounce in their certain spot and they never move. And if they don't move, it means there's no current. And that's what we see if we remove the battery in our conductor, there is no current. It's because even though the electron keeps bouncing, ultimately they stay in their same spot and they never leave. I hope that it's clear because that is important in understanding what drift velocity is. So let's say now, so that's what I just discussed here. I'm not going to read that, I'm just going to explain it. So in the end, oh no, not in the end. So what if we added back the battery? What happens to the electron? What happens to these moving electrons? So if we added the battery, there would be an electric field, right? And since we are dealing with an electron, that electron, when we apply an electric field, should feel a force opposite the direction of the electric field because simply because it's an electron. And we know that the electric field moves from positive to negative. And if the electron moves towards the negative, that's impossible because it should go opposite the direction of the electric field because it gets rejected by the negative where the electric field is going. So these electrons starts to feel a force or they exerted a force opposite the direction of the electric field. And what happens is that they start, because of the electric field, they start to slightly follow a different path. So if the gray line right here, the gray arrows were the original path that the electron is moving, if that is the original zigzag motion that is following without the electric field. After adding the electric field, which happens after we hooked up the battery, our electrons would start following a slightly different path. And you can see it here with our little goldish color arrows. So instead of moving here, our electron would move a little to more to the right and bounce here, and you can see it's a little more to the right as well. And in the end, after it keeps moving, ultimately it's on a different position. So you can see this is the original position after it keeps moving and moving. And right now, after we added the battery, after our electron starts to feel the force, it starts to move in a different path. It starts to shift a little bit towards the direction of the force. Adding all these little movements of the electron over time, we would see that the electron would now start to move. Again, as we keep the battery hooked up and as the electric field keeps moving, the electron would keep experiencing a force opposite to the direction of the electric field. And as it keeps feeling that force, it will start to move little by little. And what happens is this. So this is your original area now. So after a certain time, after we hooked up the battery, after experiencing an electric field and an electric force, the original area now, instead of here, it sort of move it from here. So this movement, this drift is what we call a drift velocity. So you can see the right here, right? So this random movement, originally without the battery, it stays the same. It stays on a relatively same spot where it keeps bouncing and bouncing. But over time, after adding the battery, the electron would start to move. And this is true for all the electrons. So slowly and steadily, these electrons, the area that they're moving, will start to move in the direction of the force that they're experiencing. And now that we have our electrons moving, if the electrons are now moving in relation to our conductor, the conductor will start to produce a current, and that's what our current is. So this drift velocity of our electrons would result in a current. And as I mentioned, it is very slow and very steady. It's because the drift velocity is actually constant. So why is it constant? The battery is now accelerating the electron towards the opposite direction of the electric field. So is the why is the electron at a constant drift velocity if it's being accelerated by the battery? It's because the collision between the electrons and the collision between the positive ions slows down the electron. So even though the battery accelerates it, the collision that the electrons are experiencing as they bounce on each other decelerates it. So in the end, there's a balancing between the acceleration and the deceleration of electrons. And this balancing results in a constant drift velocity. Therefore, the question earlier, why, if the battery is accelerating the electron, why is the current not increasing? It's because of the bouncing movement or the collision, and that results in a constant drift velocity. If we have a constant drift velocity, then we would have a constant current. I hope that's clear. So that is drift velocity. So now let's discuss how can we measure or how can we express electric current in terms of drift velocity. First, let's remember, as I mentioned again and again, that the current is the amount of charge flowing per second. Now let's think what things do affect the current. So we have another picture right here. It's the same. So we have the positive terminal of our battery. We have the negative terminal of our battery right here. We have our electrons. And we know if we hooked up the battery, our electrons would accelerate following or opposite the direction of the electric field. And that movement is steady and slow and it is constant and it's called a drift velocity, which we usually denote as V sub D. So what things do affect the current in this type of situation? Number one, because as we mentioned, current is the amount of charge moving per second, then therefore the drift velocity affects the current. So one of the things that affect our current, number one is drift velocity. Number two is the dimensions of our conductor. The cross-sectional area of our conductor and how long is our conductor also affects our current. Why is that? Because it's the amount of charge moving per second. So the longer the distance it has to travel, means the more current it is. And the bigger the cross-sectional is, it means the more electrons that could be in there. The smaller it is, the lesser electrons could pass in the wire because it's smaller. So and lastly, the number of free electrons, which is the number density, we usually denote it with letter N, and we usually is the unit. It's actually not a unit, but it's basically number density is electrons per volume per unit volume. So electrons per meter cube. So the number of free electrons, we say free electrons is because in a conductor there are free electrons that is available to be electrically that is electrically conducive, so they start moving. We call them free electrons because there are some electrons that are stuck with the positive ions, and those electrons stuck in the positive ions do not move. They are being stuck with a positive ion basically, so they cannot move away from the positive ion. But there are some free electrons that is what is moving and causing the current in our conductor. So just remember these four things that affect our current: the drift velocity, the dimension of the conductor, the length and the cross-sectional area of the conductor, and lastly, the number of free electrons that could move, that could be electrically induced. And it is usually denoted as N, which is the electrons per volume or per meter cube or per cubic meter. So let's imagine now, what if we have a conductor? And let's look at this section, this cross-sectional area of our conductor right here, this first cross-sectional area. Within 1 second, let's imagine that within 1 second, all these electrons right here pass through this cross-sectional area. So all of these were initially on the left side of our cross-sectional area, and after 1 second, all of these electrons moved and passed the first cross-sectional area. So what we know then with the definition of current is the amount of charge flowing per second. The total amount of charge of all these electrons that pass through this area in 1 second, this cross-sectional area, is basically our current. So what we're gonna do to what we just need to do is to measure the total charge of all these electrons right here. If we measure all the charges, added them all up, the total charge is basically the current of our conductor. So before we can measure the total charge, what we have to do first is to measure the volume of the cylinder where all these electrons are now encased. So how I'm gonna rephrase that. Okay, so again, all these electrons right here, these red dots right here, these are all electrons, are initially on the left side of our first cross-sectional area, and after 1 second, they all passed that cross-sectional area. They pass through. So if these are all the electrons that pass through our first cross-sectional area, and we encase them in a cylinder, measuring the total number and the total charge of all these electrons that we encase in a cylinder will give us the current, will give us the electric current in this particular scenario. So in order for us to measure the total charge, what we have to do first is to measure the volume of the cylinder where all our electrons that pass through the first cross-sectional area are enclosed. The volume of this smaller cylinder right here where our electrons are enclosed is basically equal to the area, cross-sectional area, multiplied by this length right here. And we know that this length is actually VD. Why is it VD? Drift velocity is basically what? Meters per second, right? We know that this situation right here is just 1 second total. So the length that these electrons traveled is basically the length of the drift velocity, which is per meter second. So this length right here over 1 second is basically equal to Vd. This is the length traveled by the electrons over 1 second, and length per second is a velocity, and the velocity of these electrons is drift velocity. So the volume of the cylinder is basically equal to A multiplied by Vd. So we have it right here. So before we can measure the total charge of all the electrons inside our smaller cylinder, we must identify first the volume of the smaller cylinder where they are enclosed. So the volume of the cylinder, as we've discussed, is the cross-sectional area of our wire or our conductor multiplied by the drift velocity of the electrons. Since we have now the volume of our smaller cylinder, we can now measure the total number of electrons inside the smaller cylinder. We can do that by simply multiplying the volume to the number density. Remember the number density? The number density is not do not think of it as the total number of electrons. The number density is the number of electrons per meter cube or per cubic meter. This is a density. This is the amount of electrons per volume. So this is denoted by letter N. And each conductor, a copper conductor, a gold conductor, has their unique number density, and it's usually given in a problem. So do not worry so much about the number density. It's usually given. Unless it's being asked, then you can rearrange the equation that we're going to derive using this to solve for n. But moving on, before we start talking about that, let's just reminded why we are doing this. So what we want is the total charge of all the electrons inside our cylinder. Before we can measure the total charge, we have to identify first the volume of our cylinder. And using the volume of our cylinder, we can find the total number of electrons inside our smaller cylinder by multiplying the volume density or the number density to the volume. And lastly, after getting this right here, we can now measure the total charge of all the electrons inside the cylinder by simply multiplying the charge of a single electron to the number of electrons inside the cylinder. So we know that the charge or coulomb of a single electron is negative 1.602 times 10 raised to 19 coulombs. It's usually denoted with a small letter e. So multiplying e to nv will get the total charge of our of all the electrons inside our cylinder. So the total charge is equals to E and V, or is equals to the charge of a single electron multiplied by the number density, or the number of electrons per meter cube or cubic meter, multiplied by the area of the cross-sectional of the wire or our conductor, multiplied by drift velocity of the electron. And as I mentioned earlier, the total charge inside our small cylinder is equal to the current, because that's the number of the electron, which is equal to the total charge of all the electron that pass through the cross-sectional area within 1 second. So the current is equal to the total charge of all the electrons that pass on through the cross-sectional area. Therefore, the current I is equals to charge over time is equals to the number density or the electrons per meter cube or cubic meter multiplied by the charge of a single electron multiplied by the area of our the cross-sectional area of our conductor or wire multiplied by the drift velocity of the electron, where I is the electric currents in unit coulombs per second or ampere, N is the number density or the number of electrons per unit volume, with electrons per meter cube, cubic meter, A is the charge of a single electron, which is this, and A is the cross-sectional area for conductor, which is m squared, and Vd is the drift velocity of the electrons in meter per second. So that's how we measure the current in terms of drift velocity. That's our equation. That's an equation that I want you guys to remember. And lastly, we're going to discuss about current density. So what is current density? So current density is basically the amount of current per unit area of the conductor. We can derive the equation for the current density, which we use the letter J to denote current density using the electric current equation. So we use this right here. And current density, as we discussed earlier, is basically current per area. So J is basically current divided by here, the area. So we move the area over our current, and that's what going to give us, and that's going to give us a current density right here. So the current density is equals to our current divided by the area, which is basically equal to the number density, or the electrons per cubic meter multiplied by the charge of a single electron multiplied by the drift velocity. Drift velocity is proportional, and you can also use another equation um, by substituting the drift velocity. So drift velocity is proportional to the magnitude of the electric field E and the constant proportionality micro called electron mobility. So drift velocity is equals to micro, or the electron mobility multiplied by the magnitude of the electric field. We can substitute that and get J is equals to number density multiplied by the charge of electron multiplied by electron mobility, or the constant proportionality multiplied by the magnitude of electric field. We rarely use this. We use this most of the time, but this is just something that I want you guys to know as well. So sample problem 3.1. So let's do an equation using the first equation for current that we had earlier. So steady current of 2 amperes flows in a wire for 16 seconds. A, how many columns of charge flow through the wire? And B, how many electrons flow through the wire for the given time interval? So we are given the current, which is 2 amperes. We're given the time, which is 16 seconds. And we are being asked what is the columns, how many columns of charge flow through the wire, and how many electrons, the number of electrons that flow through the wire within that 16 seconds. So again, this number of electrons is not number density. Number density is number of electrons per cubic meter. This is just how many electrons pass through the wire, not per volume. It's just the total number of electrons. Okay, so the formula we're going to use is I is equals to Q over T. Solution, I is equals to Q over T. We can rearrange the equation to solve for Q. Q is basically current multiplied by time. So 2 amperes times 16 seconds equals to 32 coulombs. So this is the coulombs, or this is the total charge that flow through our wire. So how are we going to measure the number of electrons? So we know that there's a total of 32 coulombs that flow through the wire. We can simply multiply the 32 coulombs to the value of the charge of our electron. So, but we have to use, since we're talking about number of electrons, there's no negative. So we have to use the absolute value of the charge of our electron. So 1 electron is basically equal to negative 1.602 times 1019 coulombs. So cancel coulombs, 32 divided by the charge of the electron will give us 2.0 times 10 raised to 20. So this is the total number of electrons that flow through the wire within 16 seconds. You can see that's a lot of electrons. So it's the total number of electrons. Again, this is not number density. This is just the total number of electrons that pass through the wire. Sample problem 13.2. A current of 315 milliampere flows through a gold wire which has a diameter of 10 millimeters and a length of 25 centimeter. There are 5.9 times 10 raised to negative 29 free electrons per meter cube. Now, this is not just the total number of electrons, this is density, number density. This is electrons per volume in gold. A, what is the current density in the wire? B, what is the magnitude of the drift velocity of free electrons? So first we are given the current, which is 350 milliamperes, which is 0.35 amperes. We're given the length of our wire. We are also given the diameter of our wire, which is 0.001 meter. We are also given number density, or number of electrons per volume, which is 5.90 times 10 raised to 28 free electrons per cubic meter. What they're asking us is J, this is the current density, and the drift velocity of free electrons in the wire. So formula, J is equals to 1 over A. We know that the current density is the current per area is equals to the number density multiplied by the charge of the electron multiplied by drift velocity. So first let's measure J. Solution. The cross-sectional area of a wire is pi r squared. Don't you guys remember this? Usually if you're talking about wire, the cross-sectional area of a wire is pi r squared. So we're going to use this equation first. So we are given the I. We just have to solve for A, which is I over pi r squared. We don't have a radius, but they gave us the diameter, and diameter over 2 is equals to radius. So I over pi, d over 2 squared is equals to, plugging in the number, and we'll get our current density, which is 4.46 times 10 raised to negative 25 ampere per meter squared. Rearrange the equation for the current density and use the absolute value of E to get the drift velocity. So we know this equation right here, right? So we know that the current density is equals to number density multiplied by E multiplied by VD. So now we know J. From here, we figure out J. They gave us, and they gave us, we should know E. So E is the charge of an electron. This is something that you guys should be familiar already. If you see, when we're talking about electrons, you should immediately know the charge. Rearrange the equation for drift velocity, we'll get J over NE. Plugging in the numbers, why are we using the absolute value of E? It's because this is drift velocity. Okay, so basically this tells us the velocity. Usually we only denote negative if it's going on the opposite direction. But all of this electron is going all in one way, so we don't really need negative or positive. We don't need the direction because we know all of them are going in the same direction, so we can just use the absolute value of our E. So J divided by N, this is given, and this is something that we should know. So we know that drift velocity is 4.71 times 10 raised to negative 35 meters per second. So look at this number. It's very, 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 very small. So our electrons actually travel very slow inside a wire. So the question now that I want you guys to think is, how that if I enter the room and turn on the lights, in just one click, in less than a second, the light turns on. So how is that possible if our electron travel really, really slow? It's because we don't have to wait for the electron to travel from the switch to the light. It's because the wire that is connecting from the switch to the wire, it's full of electrons. It's compact with electrons. So the moment that you switch, the electron starts to move, and you can think of it as a marble that you have a lot of marbles in line, and they all push each other. So when you start pushing it from the switch, There's a marble that connects it from the switch up to the light, and you don't have to wait for the electrons to travel from the switch to the light because there's already compact electrons that just push each other. That's why electricity is, even though they travel really in a short distance in a very slow manner, they can feel really fast because it's compact. It's full of electrons in our wire. So that's our lesson for today. So that's electric current and that's current density. So if you guys have any questions, feel free to message me and have a good day. Thank you.